Okay, this is Dr. Williamson working on some problems for you guys. And this is the problem I've chosen. It says write the Ka expression for each of the following in water. These are all acids and they are weak acids. How do you know they're weak acids? They're not on the strong acids list I told you to memorize. And these are the equilibrium expression or the equilibrium reaction for acids in water. And they are the general format HA aqueous plus water liquid is in equilibrium with A minus aqueous plus H3O plus. Aqueous. Okay. And the equilibrium constant expression for this general reaction would be H3O plus square brackets A minus over HA. We don't include pure solids or pure liquids. That's supposed to be an L there for pure liquid. We don't include pure solids or pure liquids in the equilibrium constant expression because their concentration is in large excess. I mean, their concentration is effectively constant. Okay. I'm not going to get into the reasons behind that, why it's not included. Just for now, we're just going to know that it's not included. Okay. So for this one, for letter A, HCN, we're going to have HCN, where H is obviously the H part, and CN would be the A minus part. So we have HCN, aqueous, plus H2O, liquid, is in equilibrium with CN minus aqueous plus H3O plus aqueous. And you see that this CN minus is equivalent to this A minus, right? That's the generalized form. And the equilibrium constant expression for this, Ka, would be H3O plus brackets Cn minus square brackets HCN there. Okay. And what's happening is I'm going to turn this around a little bit. H here, C, N. And on my water molecule, I got oxygen, hydrogen, hydrogen, lone pair of electrons, little cloud of a lone pair of electrons here. If I do the Lewis structure, a little cloud of a lone pair of electrons here. This is kind of a polar covalent bond where the hydrogen is electropositive because it's got some electrons pulled away from it, as the nitrogen is pulling electrons away from the carbon. And the carbon, therefore, is pulling some electrons in this covalent bond away from the hydrogen. And so these electrons are attracted to that slightly positive hydrogen, and it ends up jumping off over here. So what we end up with, if I were to kind of expand this a little bit, I would end up with basically this lone pair of electrons, dot, dot, lone pair of electrons, dot, dot, and I would have that H. That would be this guy right here, would be right there. Okay, that's what's going on. You want to know that the lone pair of electrons, even though oxygen doesn't have a negative charge on it, that lone pair of electrons, which is negatively charged, the molecule doesn't have a net negative charge, but that region is negatively charged, and it'll be attracted to that slightly positive hydrogen there. And you're going to want to know that for organic chemistry. And I am not an organic chemist, so I don't want to go much further than that. Okay. Next, HCO3 minus. So I've got HCO3 with a minus charge, aqueous, plus water, liquid. This could act like either an acid or a base. Here, we're presuming it acts like an acid where this hydrogen ends up on this water. So we're going to end up with CO3, 2 minus, you have to keep track of that, aqueous, plus H3O plus, aqueous, and the Ka for this is going to be H3O plus. You got to have the charges correct. If you don't have the charges correct, you're wrong, right? CO3, 2 minus, over HCO3 with a minus charge. And what's going on here is, let me do this, H, carbon, and I've got, 3 oxygens attached to that. I'm just going to write, oh, this is going to look sloppy, but I'm just going to write O3. Okay, it's kind of sloppy, but this is going to be slightly positive because these oxygens that are attracted to that carbon are hogging the electrons away. I don't even know if that's anyway, they're hogging the electrons away from the hydrogen. And my water, I don't even know if that's a covalent bond or not. Okay, anyway, and we're going to have our water molecule. I don't know if that's kind of in a, it's not ionic, not covalent. I mean, it's kind of in a, I'll just be quiet. Here, lone pair of electrons here. This negatively charged lone pair of electrons will be attracted to that slightly positive hydrogen. And then I end up with that same situation where I have my water molecule. I'll draw it over here. Lone pair of electrons, lone pair of electrons, right? And then I've got my hydrogen with a plus charge. That came from, the other molecule. So I'll put that there. That's what we mean by H3O plus. Okay. Let's do the next one. It's important you know that stuff, guys. Okay. The next one was H. Oops, wrong color. I wanted to use black for this just because H C O O H. Turns out this is the H that's going to come off. I'm not going to get into why. Aqueous, because I can't teach everything all simultaneously. Plus, I don't remember everything all simultaneously. H2O liquid, equilibrium. We're going to end up with HCOO minus aqueous plus H3O plus aqueous, right? It was messy. Got a plus sign here. Ka for this guy will be equal to H3O plus HCOO minus over HCOOH. Okay, kind of straightforward. All right. Something else I want to show you that we're going to use for buffers later. We could do it to all of these. I'm just going to show you here and here. I'm going to erase these others too, but the same principle applies. Okay. Is if I take I'm going to use this stuff right here. So I'll leave these equations here. I'm going to take the logarithm of this, the log of both sides, log of both sides of that. So I'm going to do this one first, put a check mark. Log of Ka will be equal to the log of H3O plus A minus over HA. You're like, well, who cares, right? Well, I do, and there's a good chance it's going to show up on the test, so you do. I'm going to use a property of logarithms where log of A times B is equal to the log of A plus the log of B. And I'm going to expand this. So I'm going to say the log of H3O plus plus the log of A minus over HA. That's equal to the log of Ka, the log of Ka. Oh, really sloppy today. Log of Ka. All right. And I'm going to use this space here. Erase that because you've got it written down in your notes. I'm going to move this to the other side of the equal sign and move that to the other side of the equal sign. So I'm going to end up doing, let's see if I can do that. No. All right. So I'm going to end up doing this. I'm going to move this over there. I'm going to move that over there. And you guys know if they swap sides, you know, if I subtracted or added on the other side of equal signs, that they change their sign. So I'm going to end up with minus log of the H3O plus I moved this over, so I left it in red, so you see it's one of the guys that I moved, is equal to, and if I move this over to the other side, that becomes minus the log of the Ka plus the log of A minus over HA. I'm going to put parentheses around that so we know it's one unit. We recognize this minus log of H3O plus. We recognize that. That is the pH, where P means the power, and this means the H3O plus concentration, the power of the H3O plus concentration. Minus log of the Ka is called the power of the Ka. Well, it's called pKa. Plus, we have this other stuff. Log of A minus over HA. Okay. This format, I'm changing the formatting and stuff like that. What color do I want? I want dark green. This is called the Henderson Hasselbalch equation. And that lets us calculate the pH of something called a buffer. And we're going to be using that in chapter 19 shortly. So if I were to apply that to this, I'm not going to go through that whole derivation all over again, but if I were to apply that to this, I would end up getting, let me erase this jazz. I would end up getting for this equation right here, I would end up getting the pH. Ooh, that's too thick. I would end up getting, come on, the pH. If I had a beaker of this solution and I wanted to know its pH, that would be equal to the pKa, would find the Ka, and I would take the logarithm of it. Plus the logarithm of the Cn minus concentration divided by the HCN concentration. Right? It's called the Henderson Hasselbalch equation. This is the, let's do this. Be patient with me, guys. I'm taking time and effort, to try and teach you guys this stuff. So this is the conjugate base. That's the conjugate acid. The Henderson Hasselbalch equation basically says for a buffer, I'll put it in words form, right? That the pH for a buffer system will be equal to the pKa plus the log of the conjugate base divided by conjugate base concentration divided by the concentration of its conjugate acid. Okay, you're going to need to know that stuff. Just thought I'd throw that in there for extra learning. Okay, I hope that helps. Do some more later.